Welcome to a new series on implicit differentiation, where we will focus on deriving stuff implicitly, you could say. But don't get this confused with partial derivatives, because we will be using equations that will have both x and y values in it. And I know if you've done partial derivatives and you haven't done this before, don't get confused. This is different entirely. So, okay. Let's get into this. So let's go to a basics for a minute. We have a y and an x. So we have the function is y and it equals some value of x. I don't exactly know what the function would be, but if a graph can pass the vertical line test, which means it only hits a value along this line once. It's not like if you have something like this where it might hit 3 times. This is just it hits once. If it passes a vertical line test, it only hits once, then it's a function. This is not a function. Okay? So let's start with a simple example. That it's a function, you could just use standard derivatives to solve it, because with the 1x value, you get the y value. Okay? But when you have something that's a little more complex, let's try something like a circle. Not a bad circle, but still. You have y and you have x. Now, if we use the vertical line test, we pick up x twice. But that means with one x value, we get 2 y values on this graph. Okay? So, that's problematic. You could find the derivative. You could use the vertical line test on the top half, which would give you 1x and 1y. And then do the exact same thing. That's a bad, but that's the idea. You can do it for the top and the bottom. That's fine, because you get the values. But that takes too much time. You could just use implicit differentiation, and you could get this all together. Now, this here is, think of it as the function for this. This is what you would type in, and this is what you would get. Okay? So we're going to try and find the derivative of this to give us the slope. So how would we do that? That's what this is all about. The derivative. Differentiating implicitly. Which just means we're just going to be finding the derivative of both sides and rearranging for the derivative. It sounds complicated than it actually, more complicated than it actually is. But we have x squared plus y squared equals 25. Okay, we'll do that example because it's easy. We can relate to that. Okay. Now, first step, we're going to find the derivative of both sides. Okay, now, so we find the derivative of each part separately. And the derivative of a number or a constant is 0, so we'll just write 0. Now keep in mind, when we go to derive y squared, in partial differentiation or partial derivatives, y is another coordinate, is like y is y is your second dimension. In this case, we're not worrying about that. Y is part of x. Y isn't separate on its own. So we can derive it. It's not like a number or anything. we're going to be treating this as a function of x. Okay, so we've got derivative of x squared. We'll start with this one. Now the derivative of x squared, you would usually say, is just 2x. What's the problem with that? Well, without knowing it, you actually use the chain rule on this, because this is technically in brackets. So you bring the 2 down and you take 1 off the power, and then you just leave the x there. But if you derive the inside, you get dx with respect to dx, which equals 1. So this actually equals 2x, because dx over dx is 1. So 1 times 2x is 2x. We usually skip that step when we're doing derivatives because it's so basic. But I only bring this in because it's gonna help explain what goes on with the y. Okay. So we have x squared, the derivative of x squared. You bring the 2 down, you take 1 off the power, you leave x, the inside, the same, but then you multiply it by the derivative of the inside. So the derivative of x with respect to dx is 1. Okay? Now, on this side, we have the derivative of y squared. Now, just like before, we treat it as we're doing the chain rule. So we bring the 2 down, the y stays the same, and it's to the power of 1 because we take 1 off the power. Now, I'm not going to write to the power of 1. That's pretty bloody basic. But then we're going to multiply by the derivative of the inside. So the derivative of y with respect to x. And that's going to look like this. And we're going to have equals 0. Now, if you notice, dy over dx is the derivative. So dy over dx is the derivative with respect to dx. The derivative of y with respect to dx, which, when you're using Leibniz notation, I'll just write it over here quickly. No matter how you look about it, you have a function. This is Lagrange's. The derivative is dash. You have a y in Leibniz's, and the derivative is dy over dx. Okay, so what we've actually found here is the derivative. Now we need to rearrange this to get this on its own. Okay, so I'll just write this down here. 2y multiplied by the derivative equals 0. So we have, this is essentially 2x. Okay, what I'm going to do is bring it onto the other side and make it, so I'm going to subtract 2x from either side. Okay, so it will look like 2y multiplied by dy dx equals negative 2x. Now what I'm going to do is divide both sides by 2y, and that will cancel out on this side, and what we're left with is dy dx equals negative 2x. I brought the negative down to the middle because if it's a negative on the top or the bottom, the whole thing's a negative. And then we have 2y. Now we can cancel out the 2's because 2 divided by 2 is 1. And what we're left with is dy over dx equals negative x on y. Okay, now that there is what we use to find the slope at one of these points or wherever. So if we want to find the slope at any one of these points, we basically need both coordinates. So we need if we're looking for this top one, we need this y coordinate and we need this x coordinate, and it will give us the slope at that point. Okay? And that's why we use implicit differentiation. I hope this video helped. Leave a comment, like, share, subscribe, whatever tickles your fancy. But either way, I hope this video helped. Thanks for watching. I hope you have a good day.